How did we arrive at this type of wave drawing? Remember, when you throw a stone in the water, it starts to form something that looks like this and it keeps going further and further. This we can note as ripples, and this is how it looks like in the surface of the water in this form. Also, we forget to know that what we are seeing on the surface of the water that is going is also occurring below the surface of the water, so that we can also have it in this form below the surface of the water. All right. Now, let me say I want to draw a line from this point here. If I draw a line from this point here, I'm going to have something that looks in this form. This is a line, and then this I could call this expression, which is drawing to look like this. And I regard this line here as the surface of the water. Now, this is what I'm seeing on top of the water, which is the ripples, and this is the one that is occurring below the surface of the water, and they keep going further and further. All right, so whenever we see this diagram, we can know that this is a wave representation. Now, from what we can see on the top of the water, that is the uppermost part, is what we call the crest, and the below part is known as the trough. All right, now the distance between the crest and the trough is called an amplitude. It's called amplitude. Also, we look at what we call the wavelength. We look at the wavelength. What is wavelength? Know that what you're seeing here are the waves. Now, wavelength is when a wave completes oscillation, has a complete oscillation, or when it completes one circle. What is one circle? This here is a semicircle, 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 and semicircle. Now, a complete circle is gotten from a semicircle plus a semicircle. That is, semicircle and a semicircle give us complete circle. So from this distance here to this distance is a complete oscillation, and hence it is called the wavelength. So I could represent it from this point over here, and then take it up, and from here I note it as the lambda. All right. Now, again, in some textbook, you might not be giving it from this place to this place. They might use another direction and represent the wavelength. All right. So I could cut from here this semicircle and have a quarter circle. I could also cut from this semicircle and have a quarter circle. Remember, I'm trying to explain the wavelength. Now, if I should use this region from quarter circle and then go to this other place here, I'll also form the wavelength, which is represented with a lambda. All right, so how is this going to give me a complete circle? If you use this quarter circle over here and use this quarter circle over here, add them together, you're going to have a semicircle. Also, if you use this semicircle over here and add to this already semicircle, you're going to have a complete circle. So that is why it is still could be denoted in a wave diagram in this form. So this is what we call the lambda complete oscillation or complete circle. Now again, we look at the period. This period is the time taken for one complete oscillation. So the time it takes to complete one wave or one circle is known as a period. We look also to what we call the frequency. Now the frequency is how many wavelengths I'm having in 1 second. So the period is talking about the time taken for just one complete oscillation to complete. Now the frequency is how many wavelengths I'm having in 1 second. Remember that this period may not be in 1 second, because in 1 second it may complete maybe about 2 to 3, 4, 5, 6 waves. All right. Now that's how many waves I have is now what I call the frequency. But the time taken for one wave to complete on that five wave I have under 1 second is now noticed as the period. All right. So the frequency is how many wavelengths I have in 1 second. All right. So now we go over to the next one called the wave phase. Wave phase. What is the wave phase? The wave phase here is maybe from the loop of that water, someone came and saw that the wave is still at this point, and as the person is still looking, the wave keep going further and further. Now, what we note as the wave phase is the point in time where that wave is. At that point that the wave is when you look at it, or where the wave is at the particular point in time, is not at the wave phase. So this is where the wave was, the person saw it. That time that the person saw it, this becomes the wave phase. So in this our wave diagram, we can say that this juncture here is going to be the wave phase, because this is where the wave is as we are looking at it. So that's why we know that wave phase. Now that is it. Again, we are going to look at the relationship. We also note frequency, velocity, that is the speed at which this oscillation is computing. All right, the speed at which this oscillation is computing is measured in meter per second. Now, relationship between frequency and period is gotten from F equals 1 over T, and also T is equals 1 over frequency. This is frequency and this is the period. Relationship between frequency, velocity, and wavelength. Velocity is equals to frequency multiplied by lambda, which is the wavelength. Now, frequency can now also be written as velocity over lambda, making sort of formula. Also, lambda can now be represented as V over frequency, that is making frequency sort of formula. Now, this is where we're going to stop in this video. There is a video I made about the equation of wave motion. Hope you have watched that, whereby y is equals to the A sine bracket angular velocity multiplied by 2 minus the phase angle at the S section, that is the horizontal line. This is phase angle and this is S. So this is the general equation of motion, and now I've made a video with it and solved 4 equations of motion. Now this is the class 3 of wave, so go to the second and first class if you haven't seen it before you come to this other video again. Thank you. In our next video, we're going to talk about the question on JAMB, a complete question on propagation of wave. Thank you.